we know by now that teleparallel theories of gravity are constructed out of tetrad fields, right? And which were a mu, right? And the torsion tensor, which was T a mu nu, which is equal to, if you recall from the previous lecture, is the partial mu of the tetrad field E a nu minus partial nu E a mu, right? So this is how you define the torsion tensor. So you can make teleparallel theories from these tetrad fields and the torsion tensors. So these are the two things that are required, where you can see that the tetrad field is the dynamical variable. Now, in addition, we know that the type of theories whose field equations are second order differential equations are entrenched from a Lagrangian density. And that Lagrangian density is constructed out of these things, which is TABC, TABC, and then you have another one TABC, TBAC, and you have TA, TA, right? Now these things are called I hope I pronounce it right, but they are called Weizenbach invariants, right? So these things are called Weizenbach invariants. Again, the Lagrangian density is constructed using the Weizenbach invariants, right? Okay, so now let's move on. Before I do that, let me remind you that the goal of this lecture is to develop the Lagrangian density for the teleparallel theories of gravity. So let's talk about first what is called the geometrical identity or the geometrical identities. The major identity is the one which relates the Levi-Civita connection, which, if you recall, was represented with this omega mu a b, and it relates this Levi-Civita connection with the contortion tensor, which was k mu a b, and it was equal to, it was defined in the last lecture as 1 by 2 e lambda a e and nu b times your torsion tensors lambda mu nu plus t nu lambda mu plus t mu lambda nu, right? Okay, so we are just moving these indices. Okay, so this identity which relates the Levi-Civita connection with the contortion tensor, it is defined as omega mu ab being equal to negative of the contortion tensor k mu a b. And so this identity can be derived using a method which I guess let's go through it, right? So let's see, where does this identity comes from. So well, you should first, let's consider for that a four-dimensional pseudo-Riemannian manifold which is equipped with the set of tetrad fields which are E a mu, right? And with an independent random SO3 comma 1 connection, which is omega, this does not look like omega, well, omega mu a b, right? And with these, then using this, then we can define the torsion tensor as, let me use different symbol. Let's use this tau like symbol. So a mu nu of your this tetrads E and the spin connection omega, right? And it is defined as partial mu E a nu minus partial nu E a mu, right? This again, it comes from this thing, but we'll have the extra terms which are for, we also have the spin connection, right? So that's why I use this different t over here. So that would be omega a mu b minus, sorry, it is related to this field, so you'd have E b nu, and then you'd have minus omega a nu b E b mu, right? Okay, and so this is what I'll be calling the torsion tensor, and we'll also define the curvature tensor, which is R a b mu nu of the spin connection, and it is defined as partial mu omega a nu b minus partial nu omega a mu b plus omega omega a mu b E no, this is wrong. Let me rewrite this thing again. You'd have plus omega a mu, let's use another symbol, let's call it C, omega a mu C omega C nu b, and minus omega a nu C omega C mu b. Okay, perfect. So this is the torsion tensor, and this is the curvature tensor. Now, if you look at this equation for the torsion tensor, you can see that it can be solved for this omega mu a b, right? So you can solve this torsion tensor equation to obtain omega mu a b, right? The spin connection. Okay, so if you take into account the anti-symmetry for the spin connection, which just means omega mu a b is the negative of omega mu b a. So this is the anti-symmetric nature of the spin connection. If you take this into account, then you arrive at an equation which is omega mu a b being equal to omega mu a b of the field E plus this, let me write it and then I'll define it later, right? So plus I'll use curly k, or let's just call it capital Kappa or whatever, mu a b, right? Now this k mu a b using the same definition for that contortion tensor, right? So this is the contortion tensor with the where you include this spin connection as well. So then this is then using that same definition is defined as 1 by 2 e lambda a e nu b times the torsion tensor t or this tau, right? Lambda mu nu plus this torsion tensor nu lambda mu plus this tau mu lambda nu. Okay, perfect. So from here it turns out that the arbitrary connection omega mu a b plays absolutely no role in the dynamics of the tetrad fields in the theories of teleparallel gravity. And so that means then we can demand that this omega mu a b is equal to 0, as it has no significance in the dynamics of the fields, right, where the field is the tetrad dynamical field. So with this then the torsion tensor, which is tau a mu nu, it will reduce it will go back to t a mu nu, which it should, right? Because this tau thing, it came when this spin connection was non-zero, right? If you go back over here, you look at this equation for the torsion tensor, and you see we included the spin connection, and that's why you had these two extra terms when you compare it with this equation over here. So it's absolutely correct, right? So it makes perfect sense that when your spin connection is set to 0, and that is because it does not have any significance in the dynamics of the field, in the teleparallel gravity, we ignore it, and if you ignore it, then your tau a mu nu reduces back to the t a mu nu. So your torsion tensor is now again defined using this equation, right? Okay, so if you keep this in mind, then your this equation for the contortion tensor will also reduce back to this equation for the contortion tensor, right? Okay, cool. So then similarly, the covariant derivative of the tetrad fields with respect to the Christoffel symbols and the Levi-Civita connection omega, it will also vanish, and so we can write that down as d mu e a nu is equal to partial mu e a nu plus omega a mu b times e b nu minus the Christoffel symbol sigma mu nu e a sigma, and it vanishes, so we'll just set it equal to 0. Now, well, the reasoning for this, for me doing this, is so that we know from the first postulate of the tetrad fields that the derivative of the tetrad field is 0, right? So partial mu e a nu is equal to 0. So this is it's called the first postulate of your tetrads, right? And it just says that the derivative of the field is 0. So now if I lower the index in this equation for the covariant derivative, and I multiply the whole equation throughout by the by this thing, right? So let me just write it over here. If I multiply this equation with e a lambda, and I'm also lowering the indices, so doing so will arrive at an equation which is let me write it down, e a lambda partial mu e a nu, which is equal to the Christoffel symbol lambda mu nu minus e a lambda omega mu a b times e b nu, right? So we obtain an expression for this thing, and if you note, this is the left hand side of this equation, which is this one, is it is the Weizenbach connection, and I'm going to now label it as this. I'm gonna use this Christoffel symbol with a tilde on top of it, and yeah, so you'll just label it as this thing, right? And you this connection, it is also called the Cartan connection, right? So it's called the Cartan connection. Okay, cool. So then I can write down the Cartan connection as this thing being equal to your normal christoffel connection, mu nu, plus the extra term for having a Cartan connection is simply your field multiplied by the contortion tensor, mu a b, or in fact it is also multiplied then by b nu, right? So you could say that it is sandwiched between the contortion tensor is sandwiched between the tetrads, right? Cool. So now using the identities that I have written over here, what I can do is I can write the scalar curvature density, which is simply, it is defined as E times R of E being equal to E times E a mu E b nu times R a b mu nu of omega, where again this thing is just your Riemannian tensor, right? So well, now if I use this Cartan connection, this equation in this expression for this E times RE, if I put it in this equation, what I get is my E times R of E is equal to negative E times 1 by 4 TABC times TABC. Again, note that this is that Weizenbach invariance, right? And which is what we need to construct the Lagrangian density, as I have already mentioned in the beginning of this video. So we are getting somewhere, right? So let's keep going. You have 1 by 2 TABC TBAC minus TA. So you have all those Weizenbach invariants, and then you have plus 2 partial mu of E times T mu. Okay, right. So I have in this writing this expression down, by the way, I have used the fact that I can write my T alpha mu as simply T mu, where these alphas contract, right? Okay, it's cool. So well, over here, note that due to the fact that the left hand side of this equation, which is E times R of E, is locally invariant under the SO3, 1 transformations, it just implies that the right hand side of this equation is also invariant under the same transformations, which is obvious, right? Okay, amazing. Now let's finally move a step further in writing down the Lagrangian density. And for that, we'll need to talk about the field equations and the energy momentum tensor. And so what I'm going to do is I'm going to start with introducing or defining a tensor, and let's call it this capital sigma ABC. And I'm going to define this tensor in terms of the torsion tensor as 1 by 4 times TABC plus, no, sorry, this is wrong. you'll just have this TABC one time, and then you'll have you'll have BAC, then you'll have plus, you'll have a negative sign, T CAB, right? And then you'll also have another term which would be 1 by 2 eta AC T B minus eta AB T C. Okay, right. So again, eta is just your Minkowski metric tensor, right? So if I define this tensor like this, then I can also write down a quadratic combination of the torsion tensor, which is defined as if I multiply from the right hand side the torsion tensor TABC with this new tensor that I have just defined, and what I get is 1 by 4 times we don't need a bracket over here, so we get 1 by 4 times TABC, and you have plus 1 by 2 T, you have this TABC and TBAC, and you have minus TA. Right, so you can check this yourself. I have simply for this equation I've multiplied it from the right hand side with this thing, right? So yes, and now next step is using this thing. Now I'll just use this thing and I'll put it back into where is that equation? Yeah, this one. So what I'm going to do is I'm going to put it in this one. You can see that we have this thing over here as this thing. These are the same things. So this means that it is just this thing, the new tensor that we defined multiplied with the torsion tensor. So therefore I can write down this equation, or I can rewrite this equation as E times R of E being equal to simply negative E sigma ABC T ABC, and you have this term, this one, which is plus 2 partial mu of E T mu. Right, so now if you look at this equation, note that apart from the total divergence, the quadratic scalar density, which is this one, is equivalent to the scalar curvature density, which is this one. So thus we can define the Lagrangian density of the teleparallel gravity as simply being equal to, let me write it as a function of E, the tetrad field. I can write it minus KE minus I'll just use this K. This K is it is the if you have any idea about the well, you must if you have watched my videos on general relativity as a quantum field theory, you must know that this K is simply a constant, which is 1 over 16 pi times G, right? So well, so this is that constant K, and you have this term which is E sigma ABC T ABC, and the if you want to write the total Lagrangian, right, so you also have this term, which is the matter term, so you have minus the matter Lagrangian. So beautiful. So we have accomplished our goal of writing down the Lagrangian density for teleparallel theory of gravity. Once you have this Lagrangian density, there are multiple things that you can do with this Lagrangian density. For example, you could go into the depth of understanding the fermionic scattering using gravitons, right? And therefore you can write down the graviton propagator. You could also write down the vertex rules, and so therefore you can write down the Feynman rules for gravity using this Lagrangian density in with the interaction with matter, right? So with fermions. So it's a beautiful subject, and you can look into the series that I made for general relativity as a quantum field theory, where there I have even talked about I have talked about uh, the the scattering and so on. I'm going to extend that, and I'm going to derive that theory in terms of fermions as well. That's pretty much it for this teleparallel theory of gravity. As I have discussed in the beginning, I'm not going to go into the mathematical depth of this, but this is the main thing that a physicist, for example, would need. So, and like I said, from here, using this Lagrangian density, you can do many things from here.